These are the Mendip Hills in Somerset, a roughly east-west ridge about 25 kilometres long. The size of the Mendips makes it difficult to gain an overall impression of their form, but a topographic model of the area shows that the hills actually form two east-west ridges, which connect to form an elongated oval. When we combine this topography with information taken from geological maps, it's clear that these ridges correspond to a series of blue stripes, which represent Carboniferous limestones. In our field study of the Mendips, we'll look at the type of information on which geological maps of this area are based. And then we'll see what inferences can be drawn from the geological structure of the area. To map the geology, we need first to find exposures of rock. And for this, we can use quarries and road cuttings, as well as natural outcrops. And there are plenty of those on the southern flank of the Mendips. We'll start with the spectacular exposures in the Cheddar Gorge. The cliffs and caves of the Cheddar Gorge have been a popular attraction since Victorian times. They formed because limestone is a rock that's relatively easily dissolved and eroded by rain and stream waters. When observing bedded strata such as these, one of the most important features that needs to be recorded is the attitude of the strata. The limestones in this part of the Cheddar Gorge are quite well bedded. The bedding planes between the layers show up very well. And when you look at this cliff face as a whole, the impression you get is that the limestones are pretty well horizontal. But this cliff face actually gives us only a two-dimensional view. And to be really sure of the attitude of these beds, we'd need a third dimension. And that means a cliff face with a different orientation. Let me show you. And this cliff face is virtually at right angles to the other one. And it shows that the strata are actually dipping in that direction at about 20 or 25 degrees. Now, to make accurate measurements on dipping strata, you need to have a good bedding plane surface to work on. A bedding plane surface like this one, for instance. It's a bit irregular, but then bedding plane surfaces are like that. They mostly are irregular. Now, the instrument you use to make the measurements is the compass clinometer. And we'll start with a strike. Now, the strike of an inclined surface is the direction of a horizontal line on that surface. And it's quick and easy to use a piece of straight stick and to move it about on the surface until it looks horizontal. And then you can check that with the clinometer. The blue needle hanging vertically points to 0. Later on in the course, you'll find out how to use this instrument to measure strike directions. But in the meantime, I get a bearing of 280 degrees. So the strike here is pretty well exactly east-west. Now for the dip. The dip is measured at right angles to the strike. It's the angle of maximum inclination of the bedding plane surface from the horizontal. I simply take the clinometer, put its edge parallel to the bedding plane, allowing for any irregularities, and the scale is graduated so that you read the angle directly off the scale in degrees. Almost 25 degrees. So the strike here is almost exactly east-west, and the dip 25 degrees to the south. And now you can see why the strata around the corner look pretty well horizontal. It's because that cliff face is aligned parallel with the strike direction, whereas this one is pretty well perpendicular to the strike direction, at right angles to it. Well, now, the rocks here in the Cheddar Gorge are pretty well exposed. But when you're compiling geological maps, you commonly have to use information from scattered outcrops and maybe occasional quarries. And you make your strike and dip measurements as accurate as you can because you use them to help you infer what goes on in between the outcrops. When you first get into an area where the beds are dipping, It's always a good idea to get a rough estimate of the dip and strike before you start making accurate measurements. It gives you a much better feel for the regional geology, for the grain of the country, and it acts as a check on your measurements. For instance, you can get quite an accurate impression of the value of the dip just by looking along the strike and holding the clinometer parallel to the bedding exposed in cliff faces. You're far enough away from the rocks for any irregularities in the bedding planes to be ironed out. In amongst the twists and turns of the Cheddar Gorge, it's not always easy to make out the true direction of dip by eye. But dips of 25 to 30 degrees to the south and a roughly east-west strike are quite representative of the uniformly inclined limestones making up the southern flank of the Mendips. Here the rocks are beautifully exposed, hundreds of meters of limestone striking east-west and dipping to the south at 25 to 30 degrees. As you look at these towering cliffs, think about their height in relation to the thickness of the beds. The beds are dipping, and so the height of the cliffs shows an apparent thickness that's actually greater than the true thickness of the strata exposed in them. Of course, the younger strata are at the top of the cliffs, the older ones at the bottom. And the beds are dipping south, so as we go north, we'll find progressively older beds being revealed. So much for the limestone making up the southern flank of the Mendips. But what of the limestones on the northern flank? These are well exposed in the eastern side of Burrington Combe. The dip here is steeper than anything we've seen before. 61 degrees. But the strike isn't very different. It's about, or close to, 290 degrees relative to true north. And that's only about 20 degrees off east-west. The big difference here is in the dip. It's steep, and here it's to the north. Well, now, the limestones we've been looking at are all pretty grey and massively bedded. But on your geological map of this area, you'll have noticed different shades of blue that represent different kinds of limestones. So let's look at these rocks in more detail. Now, this rock is made up mainly of little spheres, and they stand out beautifully on weathered surfaces. They're ooliths. This is an oolitic limestone. This part of the Carboniferous limestone sequence here is called the Burrington oolite. Now, here, as I said, the rocks are dipping north. So if we go that way, further up Burrington Combe, we should come into older strata. Well, I'm a few hundred yards further up Burrington Combe, still in these massive grey limestones, dipping steeply to the north. They do look a bit different from what we've just been looking at, because we just had a shower, so they got wet. But otherwise, they're pretty much the same. And on a weathered surface, you can see that the rock is packed with fossil fragments. They're mainly crinoid stems, the remains of sea lilies. And when you look inside the rock, the matrix of the fossil fragments is very dark. And these features are characteristic of what's called the black rock limestone in the Cheddar area. It's quite different from the Burrington oolite. And it's differences like these that have enabled geologists to map out the different Carboniferous limestone units of the Mendips. Now, using the information that we've been gathering, I've drawn a sketch cross-section for the limestones. On the south flank of the Mendips, the limestones are dipping to the south at around 25 to 30 degrees. On the north flank, they dip to the north much more steeply at around 60 degrees. So we've got quite a substantial anticline here. And the top of that anticline would make quite a sizable mountain, well over 1,000 meters above sea level. But the highest point of the Mendips is actually here, not more than 300 meters above sea level. It's called Black Down. Well, the ground up here is covered in peat and heather and gorse, and I've not been able to find any convincing exposures of actual bedrock. And that's not just because the weather's turned lousy. But there are a lot of loose blocks around up here, and they haven't obviously come from very far away, especially these bigger ones. So let's look at them. This is a reddish fragmental rock, and you can see signs of sedimentary layering in it. It's made of quartz grains. It's a quartz sandstone. This rock's quite different, much coarser, and it's got some lovely white rounded pebbles in it. They're quartz pebbles, and so we call this a quartz conglomerate. Now, the peat and heather around here tells us something else. It tells us that soil up here is likely to be acid, and that's just what you'd expect on top of sandstones. So Black Down is likely to be underlain by these quartz sandstones and quartz conglomerates. Now, when you're making geological maps, you all too often find that outcrops of actual bedrock are all too few and far between. And sometimes, like here, when there isn't any exposure, you have to make do with indirect evidence, like loose blocks and the nature of the soil and vegetation. Now, let me just remind you where we are. Here on Black Down, we're at the highest point of the Mendips, flanked north and south by the Carboniferous limestone.
This is the core of the anticline, made of red sandstones and quartz conglomerates, older than the Carboniferous limestone. And they've been identified as belonging to the Devonian Old Red Sandstone. Once, they were overlain by hundreds of meters of Carboniferous limestone, but all that's since been eroded away. There's another rock type found in the Mendips that's denoted in orange. This bears little obvious relationship to the Devonian and Carboniferous rocks. And there's a good exposure of this rock type on the northeast flank of the Mendips at Street End.
The first thing that strikes me about the rocks here is that they're nothing like the limestones we've been looking at so far. They're generally much more reddish in colour, and they've got this irregular, knobbly surface. On the whole, they appear massive, but if you look more closely, you can just about pick out these horizontal bedding planes running across the surface. And if you remember, the limestones around here actually dip quite steeply at about 60 degrees to the north. So let's take a closer look at the surface. Yes, it's sedimentary, and it's quite coarse-grained. You can see these fragments set in this red-coloured matrix. There's actually quite a wide range of grain sizes present, and some of them are angular, like this, whereas others are more rounded. But generally speaking, we call a sedimentary rock as coarse-grained as this a conglomerate. We can tell a lot more about it if we look at some of these fragments close up, where they're better exposed on the well-weathered surfaces. First of all, let's compare this conglomerate with the Devonian conglomerate that John found on top of Black Down. This is hard. The pebbles in it are white and well-rounded, and they're hard too. By contrast, this is much softer, and the fragments are grey, angular in outline, and they're softer too. Some of them contain fossils. So it's clearly not Devonian conglomerate. In fact, these grey pebbles look very much like limestone. And the fact that they're large and rather angular means they can't have come from very far away. So they're probably Carboniferous limestone. And that tells us that this conglomerate here must be younger than Carboniferous. But we can be more precise than that. These are almost certainly fragments of Devonian sandstone. So that means that the Carboniferous limestones must have been eroded down to the Devonian sandstone in the core of the anticline before this conglomerate was deposited. That puts it at about Triassic in age, and that gives us a clue as to the red colour. We know that during the Triassic, Britain was suffering oxidising arid conditions, allowing iron oxide to precipitate out, so reddening the sediments. What I need to do now is to establish the field relationships between the conglomerate and the underlying limestone. The conglomerates here are horizontal, and we know the limestone is dipping steeply. So that means that the junction between the two must be an unconformity. In the Perch quarry, I found a good exposure of the conglomerate to the left of the horizontal limestones in the north face. The knobbly appearance of this western end of the face is the first clue that it's formed of conglomerate rather than bedded limestone. Scattered red patches help confirm this initial impression, so the next step is to locate the junction. Here's the knobbly conglomerate on top. Here are the massive beds of limestone underneath. Now you notice that the conglomerate is much more yellow in colour here. This is just due to local variations in the oxidising conditions at the time the conglomerate was deposited. But the relationship between the conglomerate and the limestone is much more interesting. This is the north face of the quarry, so we're looking at the strike of the limestone beds. And we know that they're actually dipping to the south, like this. Now, if the conglomerate's horizontal, as it is at Street End, then the junction between the two must be an unconformity, as I predicted. Now, if the conglomerate's horizontal, then I'd expect that this junction, this unconformity, will be horizontal too. Well, let's follow it round and see what happens. I can trace it round here, and then down, but it seems to come to an end about here. Now, this is just a bedding plane in the limestone. And I can follow that bedding plane round. So we've got massive limestone here, but this is conglomerate. So that means the junction between the two must go vertically up the quarry face. Further up, the junction cuts diagonally to the right across the strike of the limestone beds. Since the conglomerate thickens towards the left, it's clearly been deposited against a slope in an ancient limestone landscape. The junction, in fact, traces out one side of a pre-existing valley cut into the Carboniferous limestone. During the arid Triassic period, there were occasional torrential rainstorms causing flash floods, which carried weathered limestone and sandstone debris down into the river valley. A series of these debris flows eventually filled the old valley with conglomerate. But that's not the end of the story. Further to the west, present-day erosion is cutting a new valley, down through the conglomerate. So the Carboniferous limestone landscape is being exhumed, and eventually the ancient limestone valley will reappear.
The junction of the conglomerate with the limestone in this valley cuts across the strike of the limestone. And this unconformity is a sure sign that the conglomerate was laid down after the limestone had been deformed and eroded. If we take a wider look at the Mendips, we see that virtually all the old river valleys in the limestone flanks have been filled with conglomerate, and that in the west, most of the core of the anticline was also eroded and covered with Triassic debris. From the information we found in the field, and from that contained in the geological map, we can reconstruct the main stages in the geological history of this area. At the end of the Carboniferous period, strata were folded into an anticline. Even while uplift was taking place, erosion was wearing away the limestone of the anticline, eventually exposing the Devonian sandstone in the core. Later on, during the arid Triassic period, debris flows accumulated in the valleys, and as we've seen, present-day erosion is now scouring this conglomerate out of the valleys, and it continues to wear away the anticline.